In Lesson 2.5, Implicit Differentiation, we will learn how to differentiate a function that is defined implicitly rather than the explicitly defined functions that we've been dealing with ever since we learned about functions in the first place. Of course, before we learn about implicit differentiation, we should first try to realize the difference between an explicit and an implicit function, and then we'll know when to correctly use implicit differentiation as opposed to the other methods that we've already learned. Fortunately, at this point, you've already learned about the chain rule because the chain rule is a very, very, very integral part to understanding implicit differentiation. So before we get into any of the notes or any of the examples, let's go ahead and define the difference between an explicit and an implicit function now. So in this quick exercise, I'm going to show you 5 functions, and we're going to try to determine whether each function is explicit or implicit. Now, explicit is not a term that's usually used in mathematics, and that's simply because most functions fall under that category anyhow. Essentially, explicit means that one variable is defined completely in terms of another variable. Almost all math that you've done so far has been explicit. Y equals x plus 3. If you know the x, you plug it in, you get the y. That's explicit. Easy. So let's take a look at our first function right here. And you'll see that this function is actually defined by the f of x notation. F of x equals quantity cosecant quantity x squared all to the fourth. And if you take a look at that, if I know what x is, can I find out what y is? And of course here, y is f of x. But if I know x, can I find y? And the answer to that clearly is yes. And for that reason, we're going to say that this is explicit. Now, anytime you see this f of x notation, that's pretty much telling you that it's going to be explicit anyhow. But be careful, because when you advance further in mathematics, you'll start to see functions of more than just one variable. If you see something like this, then we could say that z is defined explicitly in terms of x and y. However, that's beyond the scope of this class, and you'll hopefully have the chance to learn about that later. So let's take a look at our second function. There it is. Y over x equals 1. If I know what one of the variables is, can I just automatically figure out the other one? Well, being intelligent, of course you're going to say yes, but mathematically, does knowing one, can you just plug it in and just find out the other? And here that's not necessarily the case. So this is our first example of an implicit formula. This, as it is right now anyhow, cannot be written in that f of x notation. Now, clearly, we could rewrite this. We could write this as y equals 1x. And then we can convert it into this formula. So this particular implicit function can be written explicitly, but that's not always the case. In fact, let's take a look at our third function. There it is. And on this one, we have an x cubed and a y cubed, but then we have this 6xy term. Try as you might, you will not be able to write this in terms of just one variable. This is absolutely implicit. And unlike our previous example, this cannot even be written explicitly. You just have to leave it the way it is. In fact, if you want proof of this, take a look at the graph that's down on example C. That is a graph of this function. It's called the Folium of Descartes. It's a very well-studied equation in mathematics, let's say, but it certainly is an implicit formula. Take a look at the graph. Does it pass the horizontal line test? There you go. Alright, so our fourth equation, there it is. I don't know if that looks familiar to you or not. It's certainly ugly. We'll all agree with that. But, is it explicit or implicit? Well, if you know what x is, you can simply plug in the x's and then work this out to get y. This is absolutely an explicit formula, but boy is it ugly. However, I'll tell you, this would actually graph to a circle. Interesting. Yes, but this would graph to a circle. In fact, if we take a look at our last equation we're going to look at, there it is. This and this have the exact same graph. They are the exact same formula, if you will. However, this one is written in an implicit form. If I plug in x, I can't just evaluate y. Not like I could on this previous example. So there you go. Those are explicit and implicit functions. Now, if we had to differentiate our first example right here, if we had to differentiate this, would you be able to do it? I didn't ask would you want to, but would you be able to? And clearly, of course, you would. You would need the chain rule and all that stuff, but you could do that. Could you differentiate this one? Well, except for that plus minus thing, which doesn't make that huge of a difference right now. Except for that, certainly you could differentiate that, okay? But how about these implicit functions? Could you differentiate these? Well, by the end of this lesson, the answer to that will be yes. Let's take a look how. The two hardest things to remember when doing implicit differentiation is that we have to treat x and y as two separate variables. So when we do the derivative of x, of course we just get 1. But when we do the derivative of y, we don't just get 1. And that's going to lead us to the second thing that people often forget, the derivative of x. If we wanted to do the derivative with respect to x of x, I told you earlier that we would just get 1, but really the reason for that is we'd end up with that. And you can see how that would give us 1. However, if we're trying to differentiate y with respect to x, we're not going to get this dx thing. This time we're going to get a dy dx, and that does not reduce down. In fact, more often than not, that is the derivative that we're looking for. This is the change in y over the change in x, or slope, or rate of change, or derivative. So, to do implicit differentiation, we'll work out this example as we go along. The implicit function xy equals 1, which we took a look at just a minute ago. So the first step for implicit differentiation is that we have to differentiate both sides of an equation, and we have to do that with respect to x. With respect to x. So that's no different than what we've been doing, but let's see how that would treat us here. If we go ahead and differentiate this, of course, we're going to need the product rule because x and y are two separate variable factors. Neither one is a constant. So to do this, let's differentiate the first part first. That'll give us a 1 for our x, and then we'll keep our y. And then for the second part, I'm going to leave a little space here. You'll see why in a moment. For our second part, we'll keep the x, but differentiate the y. And of course, because we have to differentiate both sides, we'll get equals 0 for the other side right here. That 1 will turn into a 0. Now, here's where the problem is going to come in. Remember when we differentiated x, that was all fine and dandy, no problem, because we're differentiating with respect to x. But when we differentiate y, that is not so clean and easy. So that's going to bring us to step number 2 of this procedure. And what it's going to say is that each differentiated y is going to, because of the chain rule, each differentiated y, I don't know why I wrote with, requires a dy dx. And that's because of the chain rule. We're differentiating x, the derivative of x is 1. It's all good. But when we differentiate y, the derivative of y is dy dx. So let's go ahead and add that in here. Here we differentiated x, so there's nothing to worry about. But here we differentiated the y. And for that reason, we're going to need a dy dx after it. So again, the first step, you just treat it like normal. Use the product rule, quotient rule, whatever you got to do. Differentiate like normal. But then remember, because of step 2, any time that you actually differentiated a y, I'm not saying if there was a y present, but if you differentiated the y, you have to throw in a dy dx. And that's going to bring us to our third step, which is simply, because there might be many dy dx's floating around, we need to gather all the dy dx's together. And that might require you to factor out a dy dx or do whatever you have to do. So gather all of those together and then solve for that dy dx. Remember, dy dx actually is our derivative, so that's a pretty sweet little thing there. And you think we might be finished. In fact, over here, if I were to do this, I would get dy dx, and if everything else goes to the other side, I'll have a negative y over there, and I'll have to divide by x. So there is the derivative of this hyperbola. Feel free to take a look. You'll see that that is the case. But our fourth step, this doesn't always happen, and it didn't happen with our example here, but sometimes it will, and hopefully you'll get to see an example of that. But you might need to substitute in a y or a dy dx. Now, if this happens, you'll know, because at the end of a problem, you might still have a y remaining somewhere, where maybe earlier in the problem it told you what y equaled. Well, if that's the case, you can take that y equals and transfer it down to where y is in the solution. We'll see an example of that, so don't worry about it just yet. As long as you get these first three steps, we'll be okay. And with that, let's go ahead and start on our actual examples. So let's just jump into this, shall we? We have this nasty implicit function right here, or implicit equation, I suppose I should say. X squared y plus y squared x equals -2. And let's just go ahead and follow those four steps and see how this works out. I'll begin by differentiating this term right here. And of course, I will need the product rule for this. Remember that. So if I differentiate the first part of it, I'll have 2x, and then I'll just carry the y down. But if I differentiate the second part of it, the part with the y, what I'll have is x squared, and then dy dx. Yeah, the y kind of went away, but it was replaced with the dy dx. Now let's go ahead and differentiate this next term. If I want to differentiate the first part first, what I'll get here is 2y, and I'll carry the x. Of course, I did differentiate y there. So there's my dy dx for the chain rule. And then if I differentiate the next part, I'll simply get x squared. No, I won't. I'll get y squared. That didn't seem right. Y squared. And if I wanted to, I could write dx dx, but why would I do that? So it does equal 0 because the derivative of this constant, of course, is 0. So all we need to do now is gather up all of our dy dx's. If I do that, let's see. I have an x squared dy dx. And over here I have a plus 2yx dy dx. And everything else, everything I'm not using essentially, I'm just going to go ahead and shoot onto the other side of this equation. So it will look like that. And of course, my final step is really no big deal. I just need to solve for dy dx. That will be my derivative. And if I do that, I'll have my minus 2xy minus y squared. And I'll just divide by this factor right here, x squared plus 2yx. So there's our first step, our second step, and our third step. There's no need for the fourth step here because I don't really know what x or y or any of this stuff equals, so I'll just leave it the way it is. If I were to graph this thing, which I probably wouldn't be able to do on the calculator because it only accepts explicit functions, but I could use a computer graphing utility and graph this, and I bet that the rate of change of every point on that graph would be equal to this. So there we go. Well, that being said, let's go ahead and take a look at example B, where we will revisit the Folium of Descartes. We said previously that it was implicit, and now we're going to go ahead and try to differentiate it. Fun and exciting. So before we get into examples B and C, which both deal with the Folium of Descartes, I want you to try something real quick. Take a look at your notes. You'll have a graph, the same graph that we have right here, with a blue dot on it. Now what I want you to do is to guesstimate or try to figure out what the slope of the tangent line is to this graph at that point. Pause this video, take a look at your notes. You can use a ruler, do whatever you got to do, but see if you can find the slope of the tangent line to this graph at that blue point. You only really need to guess. You don't need to take it too seriously, but write your guess out to the side so we can take a look at it later, because we are about to find the real rate of change of the Folium of Descartes at that point. And here's how we're going to do it. In example B, we're going to differentiate this function that we've already seen. So I'm not going to spend a whole lot of time on this. If we differentiate the x cubed, of course, we'll have 3x squared. Differentiate the y cubed, we'll have 3y squared. But then, of course, don't forget about your dy dx. Now, when we differentiate this negative 6xy, we'll have a minus 6y. That's if we differentiate the x part. And if we differentiate the y part, we'll have minus 6x. Of course, don't forget dy dx. And all of that will just equal 0. So I'm going to skip all the algebra that's involved here and skip straight to the solution. You, of course, should pause this video and work this out on your own to make sure that you have it right. But if I do this, I should end up with a negative x squared plus 2y. That will be my numerator. Of course, I have factored out and canceled a whole bunch of 3's to get to this point. And on bottom, we should have negative 2x plus y squared. And again, you might write it a little different. Maybe you like to put the positive terms first. But this is still what you should get, somewhere along these lines. That is the derivative for the Folium of Descartes function. Now, example C just tells us to do what you already did. Try to find the slope of the tangent line right here. And considering I can't draw a straight line, that certainly will be of no help at all. But you might have said pretty much any slope between maybe 1/2 and 3/2 would be reasonable. However, the truth of this, if I evaluate dy dx, if I evaluate that at the point 4/3, 8/3, what did I do here? I drew this vertical bar. That vertical bar simply says evaluated at. That's really all it says. We'll see that bar more as we progress through this course. But we're going to try to find the derivative at the point 4/3, 8/3. And of course, you can plug those numbers in and come up with the answer. You can do it by hand, and it's a big pain. My advice, of course, store 4/3 in your calculator as x. Store 8/3 in your calculator as y. And then all you really need to do is just type this in. You have to type it in correctly, of course. Don't forget that it's better to use too many parentheses than not enough. Anyhow, if you do all this correctly, what you should get for the slope of the tangent line would be would be 4/5. So that's how we can use implicit differentiation to then find the rate of change of an implicit function, just like that. Notice this is an implicit function. It fails the vertical line test at quite a number of places. So certainly it's not an explicit function, but we can still find the rate of change using implicit differentiation. Good times. So with that, let's take a look at example D, which will certainly scare you because it has trigonometry. Let's take a look. So in example D, we have this function, implicit function, 2 sine x cosine y equals 1. If you are able to graph this implicit equation, it's actually a pretty cool graph. You should take a look. I'm not going to spoil it for you. I'm not going to show you the graph. But if you go online, you can download any one of the computer graphing programs. I highly suggest and always use WinPlot. It's free, very powerful, and can graph this equation no problem, and the graph is cool. But I'll quit harping on that for right now. What we need to do is differentiate this function, this implicit equation. And how are we going to do that? This is nothing special. There's nothing tricky about this. There's trig, so what? Let's take a look. We're clearly going to use the product rule because there is one product and there is another. So let's just let them take turns. We'll start with the x. If we do that, we'll have 2 times the derivative of sine x, which is just cosine x. And we'll just drag the cosine y along with us. And then if we differentiate the cosine y part, well, that will give us 2, we'll bring the sine x along. And then what's the derivative of cosine y? That, of course, is negative sine y. But what am I forgetting? Well, we just differentiated a y, so I better include a dy dx here so as not to lose what I'm doing. And it will equal 0, of course, on the other side. So, again, I'm not going to go through all the algebra of this. You can certainly work it out yourself. But what we are going to get if we do this is actually negative sine x sine y divided by positive cosine x cosine y. And that looks pretty ugly. And if you want to, you can of course simplify this. That's no problem. What we would end up with here would be negative cotangent x cotangent y. So the derivative really is not that difficult. We just need to make sure that we're dealing with an x and y that actually exist on the original graph. And again, if you graph it, you'll see what their graph looks like. It's pretty cool. And with that, let's take a look at example E. So perhaps example E looks deceptively easy. I mean, compared to some of the equations that we've done so far, we're just here dealing with y squared minus 2x equals 3. And I'll tell you, it is pretty easy, but do be aware that we're actually looking for the second derivative of this implicit equation. And I will tell you anyway, before we even begin working this out, that the answer is extremely simple. It's simply negative 1 over y cubed. How did I know that? Because I've done this problem already. But let's go ahead and try it together, and I'll show you where it came from. We'll start with just differentiating once with respect to x, this implicit equation. And you should have no problem doing that. We've already done enough where you should be able to get this. So when we differentiate the y squared with respect to x, of course we'll just get 2y along with our dy dx. When we differentiate the negative 2x with respect to x, that's just going to be minus 2, and this will just be 0. So is it really that easy? Is dy dx really just equal to 1 over y? And I'll argue with you that yes, that actually is the case. The first derivative with respect to x of this implicit equation is just 1 over y. So that was pretty easy. However, remember that what we're actually looking for is the second derivative. So if I want to go ahead and differentiate this is my new equation, and I want to differentiate that with respect to x, well, watch what's going to happen. On the left side here, this is where we get our notation d squared y over dx squared. So hopefully that explains why we use that as our second derivative notation. But what's going to happen over here on the right? Well, I'm going to rewrite this as y to the negative first power. That way I can avoid needing to use the quotient rule at all. And if we do that, then I'll just get negative 1y to the negative second. But of course, I did differentiate with respect to y, so I do need to include a dy dx there. Alright, well, that looks like a pretty good answer. There is our second derivative. But what's weird is that I told you that the answer was negative 1 over y cubed. Where's the disparity? Well, go back to your procedure for implicit differentiation and look at step 4, because we're going to use that now. If we look at our second derivative equation here, which I'm going to rewrite as negative 1 over y squared dy dx, do we know what y or dy dx is? I'm going to argue that we absolutely do. In fact, right here, it is stated very clearly that dy dx equals 1 over y. So what am I going to do? I'm going to plug in 1 over y for this dy dx, and look what I get for my result. There we go. Now I'm happy. So remember that when you're doing implicit differentiation, when you think you've gotten to the end of a problem, look back and see, do you already know what y equals? Do you already know what dy dx equals? And if so, go ahead and plug those in, and you'll get answers that are much easier. Furthermore, if it's a multiple choice part of a test, this right here in this red box probably will not be one of your choices. But I guarantee that negative 1 over y cubed will, because it's the correct one. So with that, let's just do a little proof to end this lesson with example F, where we're dealing with the most famous implicit equation that I know of, the circle. The great thing about calculus is that proofs are no longer like the two-column geometry proofs that you did a few years ago. In calculus, as in algebra, a proof can simply be showing your work and arriving at a result that you originally were hoping to get to. Of course, a true proof is much more rigorous than I'm making it out to be, but for the purposes of this course, let's take a look at this proof here. We have a circle that is centered at the origin. So we have the equation x squared plus y squared equals r squared. R in this case, of course, is a constant. So let's define a normal line. This word will come up again later in the year, and you'll probably ask, wait, I forgot what a normal line is. So here's what it is. Commit this to memory. It's easy. A normal line is simply perpendicular to a tangent line. So where a tangent line shows the slope of a tangent line to a function, a normal line would just be the line that crosses right through a function, in essence. So what we're going to show here is that every normal line given to this particular circle passes through the origin. Now clearly we can show this using geometry, or we can draw pictures and say, oh, well, you know, here's a circle, it's centered at the origin, and no matter what tangent line I draw, it's clear that the normal line for it will hit the origin. And you could say, oh, well, here, let me draw another tangent line. Oh, that's a nice one. And the normal line to that, again, passes through the origin. But those aren't the kind of proofs we're doing here in calculus. So let's actually find a few things out. The first thing that we should try to do is to find the slope of any tangent line to the circle. And to do that, we'll just implicitly differentiate this. That would just be 2x plus 2y y prime equals 0. And yes, I am changing notations here. You can use dy dx, you can use y prime. They can be used interchangeably. And for now, I'm going to use the y prime. So if we do a little bit of algebra, what we'll get is that y prime is actually negative x over y. In other words, the slope of any tangent line to a circle centered at the origin, regardless of the radius, is just going to be negative x over y for whatever point on that circle. Well, if that's our rate of change, that's the slope of our tangent line, what would be the slope then of a perpendicular line? So the slope of a perpendicular line, which would be the normal line. Of course, that would just be the opposite reciprocal of the tangent line, so it would just be positive y over x. So that's what we're going to use. Since we're dealing with normal lines, let's use that. Now, furthermore, let's call x sub 0 comma y sub 0. Let's call this just any given point that is actually on the circle. Of course, the radius doesn't matter here because we're defining this as a point on the circle. So that's already given. Now, if we know this, let's find the equation of that normal line. And how do we find the equation of a line if we know the slope and a point? Well, clearly that's just going to be the point-slope form. So let's see what that would look like. We'd have y minus y sub 0. Then we'd have our slope. And remember, this is the slope of the normal line. So that's y over x multiplied by x minus x sub 0. Alright, that doesn't really help us too much, but let's get this into a slope-intercept form. Because if we're trying to prove that this line is going to pass through the origin, think about what that says about its slope-intercept form. What must its intercept be to pass through the origin? If you don't know, hopefully we're going to find out here in just a moment. So let me just carry out some work here. Again, I've told you that you really don't need to simplify, but for the sake of this problem, it might be a good idea. So when I multiply the y over x times x minus x sub 0, this is what I'll get. Of course, these two x's cancel out. And all I need to do now is solve for y. So if I bring this y over here and bring everything else over, well, that would give me 0. Yeah, because I have a positive y here and a positive y here. So that's kind of interesting. And what will I end up with over here? Well, it looks like negative y x sub 0 over x plus y sub 0. Well, that's very interesting. I kind of wanted to solve this for y. So let me go ahead and do a little bit more work here. If I multiply everything you see by x, that'll still give me a 0 on the left, but over here I'll have negative y x sub 0 plus y sub 0. And now I can try to solve for y. If I do that, let's see, I will simply have y sub 0 over x sub 0. And there is my linear equation in slope-intercept form. But where's my intercept? Where is my intercept? Well, because there is no intercept, that tells us that we must be passing through the origin. And so we've proven that any normal line to any circle centered at the origin will have a normal line that passes through the origin, and thus it is proven. So, in lesson 2.5, we began by talking about the difference between an explicit and an implicit function, and we looked at a bunch of examples of those. After that, we talked about how we already know how to differentiate an explicit function, and so we talked about the procedure for differentiating an implicit function, which we will from now on call implicit differentiation. That makes sense. We still had to use the product rule and the quotient rule and all that good stuff, but anytime we differentiated a y, we introduced, because of the chain rule, a dy dx. So, after we did that, we looked at a couple applications of implicit differentiation, looking at the Folium of Descartes, and then looking at circles, which is something that we were already familiar with anyway, but hopefully now you see them in a new and beautiful light. So remember all of these things. There was a lot this section, and implicit differentiation is not going to go away. It will be with us all year, so get used to using it. It's just an application of the chain rule. It's nothing to be scared of. And so please remember that, and good luck with your assignment.